Taylor polynomials are widely used in advanced mathematics, and it can be really helpful to know them from memory. But the formula is a bit hard to remember. Here's one way of looking at them, which might help. Instead of memorizing the formula itself, I'm going to memorize an intuition for Taylor polynomials, what they are and how they work. This is easier to remember than the details of a technical definition, but will guide us to correctly remember the formula. So, the intuition for Taylor polynomials I commit to memory is this. Taylor polynomials approximate differentiable functions by ensuring the derivatives match at a certain point. How are we going to achieve this? Well, we're going to construct a sum of polynomials such that the nth order polynomial I add has the same nth derivative as my function. What do I mean by this? Well, take this function for example. At x equals 1.5, the function has the following value and derivatives. What I want for the Taylor polynomial is a polynomial which has the same value and derivatives at this point. Let's break down a single term in the Taylor polynomial and see what happens when we differentiate it n times. Since these terms are just numbers, we can pull them out of the derivative, and we're left with differentiating this polynomial n times. Note that it's an nth order polynomial, and since differentiating a polynomial reduces its order by 1, we should end up with a constant after differentiating. What happens when we take the first few derivatives? Well, using the chain rule, we just pull down the power and reduce the power by 1. If we do that again, we get n times n minus 1 times x minus a to the power of n minus 2. And we have a pattern here. If we differentiate this polynomial n times, we just end up with n factorial. So if we consider our nth term in the Taylor polynomial, these n factorials will cancel out, and we're just left with the nth derivative of the function at the chosen point. In other words, this nth term has the same nth derivative as the function. Now let's look at what happens to other terms in the Taylor series. We know that when we differentiate this sum n times, this term will give us the nth derivative of the function at a. But what about the other terms? Well, all these terms to the left of the nth term are of order less than n, so if we differentiate them n times, they vanish. To convince yourself of this, consider taking the third derivative of a quadratic, or the fourth derivative of a cubic, and so on. What about the terms to the right? Well, since they have order greater than n, when we differentiate them n times, we will have at least one power of x minus a. So if we consider the value of these terms at the point x equals a, we have at least one term, a minus a, which is 0. So all these terms to the right also vanish. So what we see is that even when we consider these other terms in the sum and take the nth derivative of the whole sum at x equals a, every term except one of them cancels out, and this term gives us precisely the nth derivative of the function at a, by design. So if we think about it this way, the Taylor polynomial formula really just gives us the construction needed to create a polynomial approximation of a function, ensuring that the derivative values match at a certain point. Hopefully by making sense of Taylor polynomials in this way, you might find the formula easier to remember. Instead of rote learning a formula, we can remember an intuition for Taylor polynomials, and use that intuition to remind ourselves of the formula whenever we need it. Thanks for watching. If you like this style of video, let us know down below, and don't forget to like and subscribe to support Learn a Lot. Until next time.